Hey guys, welcome. Yeah, so today's a good day. Thank you, Lord Jesus, for crushing anyone associated with evil and misleading children, Kobe. While working with a student today, I came across four really nice limit questions, and they're somewhat sophisticated. But yeah, if you want to see if you should stay or go, these are the questions. And so I thought I'd share. And actually, I have to board a 2 a.m. bus soon to go see my mom and take care of some biz. So let's get on with this. All right, so the first one is, have less than an hour. X goes to 0 plus, all right? So X goes to 0 from the right of tan inverse of the natural log of X. Now, there are times when you should evaluate limits using algebraic techniques, but there are times when visualizing the functions is crucial, and this is an illustration of how the latter is important. So first, notice that we have this limit rule, which is if you have the limit is x goes to a of f of g of x, right? We know that this is the same as f of the limit is x goes to a of g of x. So what I'm saying is, applying that limit rule, we can write that this is tan inverse, and then lim is x goes to 0 from the right of the natural log of x. Got it. Now, remember what the natural log looks like, right? It looks like this. The y-axis is a vertical asymptote for it, and this is 1, 0. I really only care about what's happening as we go to 0 from the right. Remember, going to 0 from the right means that you're doing this. You're going to 0 from the right towards the left. As you can see, as we go to 0 from the right, the natural log function is going down to negative infinity, right? So in theory, where we're at, we can say that this is equal to tan inverse of, remember, tan inverse is arctan, right? And then, as I just said, this is negative infinity, so tan inverse of negative infinity. Got it. Okay, cool. Now, we need to recall what the tangent inverse function looks like. And this is one of the most important functions for many reasons, so you should know it. The tangent inverse function has horizontal asymptotes right here and right here. And you should know what y values these are. This is negative pi over 2, and this is pi over 2. And tan inverse looks like this, right? It looks like, it looks like that. So what we're looking at is tan inverse of negative infinity. In other words, what happens to tan inverse is x goes to negative infinity. Clearly, as x goes to negative infinity, tan inverse is approaching the y value, negative pi over 2. It's bottom asymptote. So the answer to this, negative pi over 2. Yeah? Okay, cool. So next one. The next one is this. Lim is x goes to infinity of 1 minus e to the minus x, or no, that's just 1 minus e to the x, okay, over 1 plus e to the x. So going to infinity means that you're considering very large x values. And if you're considering very large x values, small x or small numbers like 1 and negative 1 don't matter. So right? Because we're considering really large x. So like the 1 doesn't have much effect. The numerator is dominated by this quantity and the denominator is dominated by this quantity. And so then a very simple and quick way to answer it is, since the original function is equivalent to this quotient, right? So I'm saying if I write 1 and 1, this is the same, approximately the same as doing lim is x goes to infinity of minus e to the x over e to the x. you can clearly see that this is equal to -1. So this is like if you're on a test and you're pressed for time and you just want to answer the question quickly. But what would we do if this was x squared and this is x squared? Well, in practice, what we do is we look at the numerator, we look at the denominator, and then identify the dominant term, and we divide everything in the numerator and everything in the denominator by that dominant term. So what I'm saying is if this was the question, we do lim as x goes to infinity of the dominant term. If we look both in the numerator and denominator, is x squared. So we divide everything by x squared. So 1 over x squared, and then minus x squared over x squared, right? And then it should be black if I'm staying consistent, over, and then 1 over, and then plus x squared over, and it's x squared here and x squared here. Clearly this is 1, right? And this is also 1. And so then as x goes to infinity, this goes to 0, and this goes to 0. And so we go to -1 over 1, which is -1, same answer. So we want to do a similar thing, but with e to the x this time, right, in this example. So e to the x is here, and e to the x is here. So we divide by the dominant term. So if I may, in the interest of time, just divide by e to the x here, by e to the x, right? What we've got is lim as x goes to infinity of 1 over e to the x minus e to the x over e to the x, 1 over e to the x plus 1. Again, as x goes to infinity, this goes to 0. This goes to 0. And so we go to -1 over 1, -1, right? Okay, I'm sweating so much. Okay. What is next? All right, so this is really cool. The next one is lim. Sweating so much, Lord. And then it's 3 cos x, and then sine 4x all over 2x. Okay, remember, limits have a bunch of properties, one of which is the limit of the product is equal to the product of the limits. I'm saying this. If we have lim as x goes to a of f of x times g of x, we can write instead lim as x goes to a of f of x times lim is x goes to a of g of x. So I want to exploit this property and first write we have lim is x goes to 0 of 3 cos x times lim is x goes to 0 of sine 4x over 2x. Am I acting like a man who's running out of time? Okay, so all right, this should ring a bell, and this is what I mean. Remember that really famous limit that said limit is x goes to 0 of sine theta over theta? I have a proof, a really cool proof using the squeeze theorem of that limit, right? And this is equal to 1, we should all know, right? Okay, what's crucial is that what's here and here has to be the same. So the argument of sine, whatever that is, it has to be the same in the denominator. So if I say 4x here and I have a 4x there, then that's still true. Sorry. 4x and 2x, no good. We need this 4x and this 2x to be the same, but easy fix. You throw on a 2 there, you throw on a 2 there. That is multiplied by 2 over 2, which is multiplying by 1. And now this is 4x, right? And using the other limit property, which is that we can throw a constant in front, I'm going to put the 2 right here. Now, as I just said, this is equal to 1. And we've got that this is equal to 3 cosine of 0. We had no problem plugging in 0 and cosine. And then times 2 times 1. Now, cosine of 0 is 1. So we've got 3 times 2, or 6. Okay. Yeah? Okay, cool. The box around 6 is not really good, but whatever. It looks weird. Okay, but let's keep it moving. Speaking of the squeeze theorem, the next and final example is about the squeeze theorem. And it says this: find the limit. This is our fourth one. Have I been numbering them? Well, I hope you can count. Limit is x goes to 2 of what? Of h of x plus 3 over 4. And you must be wondering, well, if you were paying attention, if you were paying attention when I had the paper in front of you, it said over 2, but whatever, same kind of deal if it's over 4. But what is this h function? They tell us that near the x value 2, for all x, h is squeezed by two functions. One of it is 2x cubed plus 5 is less or equal to h of x, and h of x is in turn less or equal to x to the 4th plus 5. Now, the squeeze theorem, which is in France called the police theorem, says this: if you have g of x is less or equal to h of x is less or equal to f of x, and you have that like lim is x goes to a of g of x is L, and lim is x goes to a of f of x is also L, then we have no choice but to say that lim is x goes to a of h of x is also L, because h is squeezed between g of x and f of x. Okay, cool. So that's kind of the deal. So we go lim is x goes to 2 here, and I'll just write it above. Lim is x goes to 2. Can I get away with that, please? Now, as x goes to 2, this becomes 2 times 2 cubed plus 5. Notice that that's 2 to the 4th plus 5 is less or equal to lim is x goes to 2 of h of x, which in turn is less or equal to this limit, which is 2 to the 4th plus 5. I see. 2 to the 4th plus 5 on here, 2 to the 4th plus 5. So that's what L is. So we see that this here is equal to, it's equal to 2 to the 4th plus 5. Got it. Okay, so where to? Well, we want to use this fact, the fact that limit x goes to 2 of h of x is 2 to the 4th plus 5. What's that? That's like 16 plus 5, that's 21, right? But we can't just yet apply it. So first, let's do this. Let's take this and say that it's the same as lim is x goes to 2 of 1/4 h of x, right? And then plus 3/4. And again, applying limit properties, we can say that that's the same as lim, well, let's take out the constant right in front of the limit, 1/4 lim is x goes to 2 of, that's h by the way, so h of x, and then plus lim is x goes to 2 of 3/4. That's a constant, so that's just, it's x goes to 2 still becomes 3/4. And then this fella, right? We already have him. He is 21. So we have 21 and then times 1/4 over 4. That makes 24 over 4.